All right, so, like I said, today we're going to be working on picking up the last part of section 4.2, moving on into section 4.3, and hopefully getting into 4.4 as we're right here in the middle of chapter 4, if you will. So let's pick up where we left off, and we were talking about, again, repeat of what we did in chapter 2.8, which is null spaces, column spaces, and row spaces. So here we go. Again, just to remind you, a little bit of review here, column space of A. The column space of A on an M by N matrix is the set of all linear combinations of the column vectors of A. So, if you look at this M by N matrix, so again, it looks like this. You're going to have, look at the columns. So if it's M by N, you've got M rows of what? N columns. So there'll be an A1 column here, an A2 column here, dot, 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 out to an AN column here. And you've got M rows, just to show you that M by N matrix type thing here. So, the column space of A is the span of all the column vectors. Okay? That's what we've done before. We went to the span of these guys. And the theorem here is that, now I got a question for you. If these vectors, this matrix is M by N, and you look at one of the column vectors, how many components does a column vector going to have in it? M or N? M. It's M by N. You've got N number of vectors, but each vector is going to have M components. So the column space of A is a subspace of going to be of Rm. M by N. You're going to have N vectors, but they're going to be M components in it, so it's going to be a subspace of Rm. Note, the column space of A is equal to the vectors B from Rm, such that B is equal to A times X for any X in Rm. So this is the way you need to think about the actual space of the column space. Basically, it's all the linear combinations of the columns of matrix A, and so you're in this particular space if you're a vector that you are equal to the linear combinations of the columns of A, which means A times X for any X element of Rm. So the column space is in the range of the linear transformation Tx equal to Ax. Back to this linear transformation. We're going back to these guys. So it's in the range. So to be inside of Rm, you're going to be in the range of the matrix A or the linear transformation Tx, which is represented by matrix A. So let me just go ahead and give you an example here. All right, so I got this right here. So I kind of wrote it strangely because, again, I'm trying to get you guys into the matrix mindset here. It says this, quote, find a matrix A such that W is equal to the column of A, where W is equal to, you've got this little vector here, A minus 4B, 3A plus B, B minus 7A, such that A and B are real numbers. Okay, what would my solution be? All right, so I'm going to rewrite W. Here's the trick right here. Well, the first thing I'm going to do with rewrite W is I like to have things line up. The book will mess you up. It's also on that computer software stuff that we typically do. Pay attention to positioning. So I've got A minus 4B. There's the A, there's the B. I got 3A plus B. The A's and the B's line up. But notice this third component here is B minus 7A. We should rewrite him. That would be negative 7A plus B, such that A and B are real numbers. So all I did was just make sure they lined up. So we can rewrite W as this. It is the vector 1, 3, negative 7 times A plus the vector, sign goes with it, negative 4, 1, 1 times B, such that A and B are real numbers. Real numbers also known as scalars. Okay? So, who exactly is W? Again, look at my transformation from this block vector thing that I had to cleaning it up. A and B are scalars. What do you call it when you take a scalar, arbitrary scalar A and an arbitrary scalar B, multiply it times a vector. What do you call that? We have a fancy name for that. The set of linear combinations, which is also known as the, all right, very good, span. So this is equal to the span, because it's the linear combinations of these two guys, of these two vectors, 1, 3, negative 7, and the vector negative 4, 1, 1. Okay. Again, this is what we're after here, trying to make the connection between everything. So, again, oh yeah, what was the question on this problem? We are supposed to find a matrix A such that W is equal to the column space of A. Well, here's the column space of A, but we want to find the matrix A. This is called the column space. So, therefore, three dots in a triangle fashion is therefore A would be equal to what would be my matrix. Well, these are the column spaces, these are the vectors, so you just got to put them in the column. 1, 3, negative 7, negative 4, 1, 1. So this would be my answer for what A would look like. Does that make sense? And you can almost see it here, except they try to mess you up by putting stuff out of order, but there's your matrix. Does that make sense? Did I lose you anywhere? All right, let me try another problem here. Try this one. All right, here's another example for you guys. Let me blow this thing up. You guys can see this one pretty good. There it is there. All right. Matrix A is this matrix. 7, negative 2, 0, negative 2, 0, negative 5, 0, negative 5, 7, negative 5, 7, negative 2. All right. If the column space of A is a subspace of RK, what's K going to be? Column space. Okay? So what do the vectors look like? They come from what? This is math, don't think too deep. It's called the column space of A. Look at your matrix A. Where did the vectors come from? What are the vectors made up of? Well, no. Key word here. Columns of space. Column space. So, what did the vectors look like? They're column vectors. Okay. Look at your column vectors. Where did the column vectors, what kind of space did the column vectors look at? How many components are in the column? 1, 2, 3, 4. You notice this matrix is a 4 by 3. Got to mess you up on the not square thing here. But the columns come from, they have 4 components. So K would be equal to 4. Because just an example here, let me show you what one of the vectors looks like. It is 7, negative 2, 0, negative 5. This is a vector in R4. So K has got to be 4. Does that make sense? Keep going. If the null space of A is a subspace of Rj, what would J be equal to? Okay? All right, how do you find the null space? All right? Remember your definition. Null space of A is basically the space of solutions. Null space, let me write this down. Null space of A equals the space of solutions of A equals 0 vector. Just to remind you of who's who. So this X is an element of the null space of A. What is X going to look like? If I multiply A times X equals 0, what do I multiply times this vector right here? Okay, so A again is this 7, negative 2, 0, negative 4, 0, negative 5, 0, negative 5, 7, negative 5, 7, negative 2. What kind of vector X would I get, and what would that 0 vector look like? So just kind of look at this guy right here. What size is my matrix? What size was this dude here? It is 4 by 3. What does that make X have to be if he's going to be a vector? 3 by, and typically vectors are always by 1. So this vector X has to be a 3 by 1 looking vector, right? And the 0 vector would actually be a 4 by 1. Think about how you do your matrix multiplication. So my question now, understanding this concept, and X is an element of null space of A, which is a subspace of Rj, what does J have to be? 3. It's going to be 3 by 1, so it's a subspace of R3. Does that make sense? Okay? Again, straight questions I can ask you guys. Find a non-zero vector in the column space of A. Find any vector in the column space of A is basically what I'm asking about. Well, look at A. Again, A was equal to the matrix 7, negative 2, 0, negative 5, negative 2, 0, negative 5, 7, 0, negative 5, 7, negative 2. Well, there's an infinite number of non-zero vectors in the column space of A, but you only have like 1 second to find one, so give me one. That could be my choice. I pick the first guy. 7, negative 2, 0, negative 5. That would work. Or you could be obstinate and take the ground in the middle, negative 2, 0, negative 5, 7. Or you could take the last one just to be different, 0, negative 5, 7, negative 2. And if you really want to mess me up and make me take off extra points, make me look at it, you could do any linear combination of these guys. Does that make sense? But that would take way more than like 1 second to get an answer out of this thing. So this is what basically I'm looking for. And this would have been my choice because then I can move on to the next problem. Okay? Got a question for you. Part D. Find a non-zero vector in the null space of A. Find the null space of A. Well, find the null space of A. What do? We take A and we augment it to 0, right? The 0 vector. And then we RREF this guy. Does that make sense? So, and what this is going to do is, let's see here, this will turn into some type of matrix, a solution, and hopefully we'll get a row of zeros on this guy. We'll end up going back and setting it equal to 0, and then we go and solve for the pivots, and they got the free variables and all the stuff you've done before. But this was always my first move, and I had to do RREF. So let me throw in there on my calculator, just to save a lot of time on this one. So matrix, edit, A, there it goes, I'm in the edit mode here. What size matrix was this guy here? 4 by 3. Okay, but if I want to augment them with one more vector, so this would look like this. 7, negative 2, 0, negative 5, negative 2, 0, negative 5, 7, 0, negative 5, 7, negative 2. You would augment it with the 0 vector, okay? But I'm going to put in 4 by 3 because I want to show you guys something or other that's going to frustrate you if it hasn't already done so. So this guy is 4 by 3, so let's just type him in here. What is it? 7, negative 2, 0, negative 2, 0, negative 5, 0, negative 7, negative 5, 7, negative 2. Okay? And I typed it in. I always do this. So I'm showing you some more math on the calculator thing here. Again, more being advantageous in our future. Second quit, I'm going to go back to matrix and just do names, call up matrix A, and I hit enter. And I always double check my matrix just to make sure that I did type it in correctly. Looks good. Now, what do we typically do with this guy? We reduce row echelon form this guy. So if I go second matrix, math, go over here to RREF on matrix A, do I get the famous invalid dimension go to quit thing here? you're dealing with matrices, what's been programmed on your calculator is this. For solving equations, to be able to get solutions, you always have to have, the same number of variables as equations, or you can have more variables than equations. But the calculator will give you a dimension mix match thing here, the invalid dimension thing here, when you have more equations than variables. Let's look at the problem that we're looking at here. Here's matrix A, that's why I wrote them out here. So if you look at this as equations, here's x1, x2, x3. We're setting it equal to 0 for the null space, right? How many equations do I have? I got 1, 2, 3, 4, because I got 4 rows. But how many variables do I have? That's the number of vectors, 3. I got more equations than I do vectors, than I do unknowns. Does that make sense? I got more equations than I have unknown. That's why you get the dimension mix match. So how do I fix it is going to be the question here. All right. How do you fix it is this. Go back to matrix, edit A, and change the size of it. Well, what are you going to put in that? Well, zeros are wonderful guys because they really don't do anything when you multiply a row by a constant, add it to another row where they're all zeros. What do you get? More zeros. So I'm going to go, because it got to be at least square, or you got to have more row by columns. You got to have more columns than you got rows to do REF on the calculator. So just give yourself some more zeros. If you need some more size, just make them zeros. So I'm going to make this thing 4 by 4, okay? And watch over here, the automatic default is to put zeros in there anyway, but that's awfully nice. And then, now you can go back and just do that RREF. Now the A is 4 by 4, it'll do it for you. Okay, but remember, that last column is a red herring column that I just put in to get the dimension mix match. So here's my point. When I do this guy, and I do RREF on him, what does my calculator give me? It gives me 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. That's what it gives me. Well, what happened to that third row of zeros? I just put that in there just so I get the calculator to do the job. Does that make sense? That 0 row is not really going to, that 0 column is not going to really do anything. Does that make sense? So, there we go. Oh, yeah. So, what was the actual question on this particular guy here? Find a non-zero vector in the null space. Well, if I augment this with 0, which I did, and I do my RREF on this guy, what am I going to get? Well, there's the RREF of the matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. You augment it with the 0 vector. What is this telling me? This is like C1, this is C2, and this is C3 here. What is C1 equal to? I remember, right back equations. What's C1 equal to? 0. What's C2 equal to? 0. What's C3 equal to? 0. So what is the X vector equal to? If it's going to solve this guy, there's only one of them, 0, 0, 0. So now, understanding this concept, that there's only one solution, 0, 0, 0, is the only vector in the null space of A. Please find a non-zero vector in the null space of A. What is the answer? There is not one. Okay. There's only the 0 vector in there. There's no non-zero vector in there. The only solution is the 0 vector. 0 vector is always in the null space. 0 times anybody is 0, so it's always 0 always solves it. What about the non-zero guys? Well, that's when you've got to have row of zeros, and you've got to have pivots, and you've got to have a non-pivot free variable. We've got no free variables, is my point. When you have no free variables, well, there will not be anything but the 0 vector in the null space. You've got to have free variables. Yeah.
So when you have a lot of equations and vectors, they would always be reproducible?
No, not always. I can screw you up and make one that you can have 1 here, a 1 here, a 4 and a 5, and a couple of rows of zeros. Oh, I can give you some free variables even on this type thing here. But to get the calculator to do it for me, I'm going to have to stick in a couple more rows of zeros to make sure it's at least square before I hit the REF button. That's the other thing I'm trying to show you guys. Yeah.
For this time C2, C3, how did you get that? Was that just kind of from the box?
it's kind of like looking at the equations here. So this is a matrix that represents equations. You augment it with zero, so you've got, you can call it C or X, that's your choice, whatever letter you want to call it, X1, X2, X3, if you like that. So X1 times 1 plus X2 times 0 plus X3 times 0 plus 0, that means X1, C1 equals 0. I'm just reading them right off. Okay? So, question for you. Is U being 1, negative 1, 0 an element of the null space of A? Well, two things. What was the answer to D? What is the only non-zero, what is the non-zero vectors of the null space of A? There isn't any. So is this guy being non-zero, is he going to be in the null space of A? No. How do I show you that? Because not only does he get the answer right, yes or no, the answer is going to clearly be no, you need to show it to him. To show, or to prove the null space to be in the null space of A times U has got to be equal to what? To be in the null space, you're equal to 0. All right, don't hurt yourself. What was A again? Oh, it's still up here. It's 7, negative 2, 0, negative 2, 0, negative 5, 0, negative 5, 7, and negative 5, 7, negative 2. What was U? This guy here, negative 1, positive 1, negative 1, 0. And I'm going to multiply it. Let's see what we get. When I multiply this thing, I end up getting row by column. 1 times 7 is 7, 2 times negative 1 is 2, 7 plus 2 is 9, 0 times 0 is still 0, so pretty much I get 9. If you do the rest of them, you get negative 2, 5, negative 12, right? But notice that this is not the 0 vector. Does that make sense? So the answer is clearly no, this is not going to be in the null space of A. It doesn't have one, there is not one. It's the answer from D there. Does that make sense? Did I lose you guys anywhere? Okay, keep going, I got more questions for you. This one, in the same context of the problem here, is V 2, negative 3, 0, 1 in the column space of A. Again, better write it down because I've changed papers here. What was A equal to? A was the matrix 7, negative 2, 0, negative 2, 0, negative 5, 0, negative 5, 7, negative 5, 7, negative 2. All right. So, I have a question for you guys. Show me what you know. How is a vector in the column space of A? To be in the column space of A, this vector, V, has to be a linear combination of the columns of A. What does that mean? This means that vector V has to be equal to a constant times this first vector, 7, negative 2, 0, negative 5, plus there's got to exist a constant C times the second vector, negative 2, 0, negative 5, 7, plus another constant C3 times that third vector, 0, negative 5, 7, negative 2. You have to find me, you need to find C1, C2, and C3. Well, remember, V is this vector here, 2, negative 3, 0, 1. How would you solve this guy? What would you do? Augment. Outstanding. Basically, you're going to take matrix A, which is this matrix 7, negative 2, 0, negative 5, negative 2, 0, negative 5, 7, 0, negative 5, 7, negative 2. You're going to augment with the V vector, which was 2, 0, 1. And now, you augment, and then what are you going to do? Okay, so let's do that. Calculator again today. I'm going to go back to matrix, edit A, because there's my A matrix, except what's 4 by 4. 4 by 4, we're augmenting it. There's the 4 by 3, there's matrix A there. So I need to come over here where these zeros are at. I'm going to put a 2, down arrow a -3, down arrow a 0, a 1. And hit enter. Don't forget to hit enter after every time you type in 1. So now I'm going to call back matrix A, and just double check it. Make sure I got this matrix right here. 7, -2, 0, 5, -2, 0, -5, 7, 0, -5, 7, 1, 2, -3, 0, 1. Got it. So I'm going to go back to matrix, math, reduce echelon form on my matrix A. Now will my calculator actually do this one for me? Because I augmented this 4 by 3 with that 4 by 1, it's now a 4 by 4 matrix, right? It's at least square, and it has to be at least square for the calculator to actually continue with the programming. And it did. And then, wait a minute, let me make it better. Convert answer to fractions. This is why we looked at T84. And there it is. So I got this. 1, 0, 0, 92 divided by 203. Now you know really why I didn't do this one by hand. Keep going. 0, 1, 0, 17 over 29. 0, 0, 1, 85 over 203. And 0, 0, 0, 0. Please tell me what this means. Yeah. All right, speak up so you have mic here. Oh, wait. What was the question? Is this vector in the column space? Now, setting equal to 0 would be the null space. We're not talking about null space now. We're talking about the column space. Is this vector in the column space? And remind you, to be in the column space, there's got to be a constant that you can multiply times the first vector, plus a constant times the second vector, plus a constant times the third vector, to be able to get that v vector. Did we find that, yes or no? We did. The answer is yes, we did. And the answer is that C1 would be equal to, remember this is the augmented part, 92 over 203. C2 is equal to 17 over 29. And C3 is equal to 85 over 203. So I found my constants. That means yes. If I could not find constants on this guy, then the answer would have been no. How would I have known that the answer would have been no? What would have been a clue for me that this answer would have been no if I did this? We took this matrix, and the V is not the 0. We got the V vector here. And when I did reduce echelon form, what would have happened? Inconsistent system. What does that mean? 0, 0, 0, a number, not 0. That would have told me right there, there is no answer. It's inconsistent, so these answers do not exist. That's how I would have said, no, it's not in the common space of A. Does that make sense? So all this stuff we've been doing is accumulating back onto this material once again. Have I lost anything? Okay, big one. Terminology. More definitions. The range and kernel of a linear transformation. Okay? Linear transformation or combination. Okay? So range and kernel of a linear combination and linear transformation. All right. First off, let's remind ourselves of what a linear transformation is, because we're going to come back and beat this stuff to death once again. A linear transformation is a mapping T from vector space V to vector space W, where V and W are vector spaces, with these properties. Transformation of vector T plus V is equal to the transformation on vector U. So the transformation of vector U plus V is equal to the transformation on vector U plus the transformation on vector v. And the transformation on the scalar c times vector u will be equal to the scalar times the transformation on vector u. So linear transformations, these were our properties. If I've got a linear transformation on a sum of two vectors, that will always, if it's a linear transformation, be equal to the transformation on the first vector plus the transformation on the second vector. And if I ever have a constant, a scalar times a vector, and I do a linear transformation on that guy, it should always be equal to that same scalar times the linear transformation of that vector. These were my definitions of when I have a linear transformation. Now, new word that you will see again, and for those people that are going to go on and take Math 3163, the modern algebra class, and that word is the kernel. The kernel of T is also known as the null space of a matrix A. Because remember, any linear transformation can be represented by a matrix. So we keep converting this world over and over, but we're dealing the world of T here, so we got special names for that. And we've got special names for the matrix A, but they're synonymous. So the kernel of T, also known as the null space of matrix A, that represents the transformation T. So the kernel of T is equal to all the vectors u from V such that Tu is equal to 0. Okay? So from V, remember, linear transformation goes from V to W. So it's in the domain, if you will. Okay? So any vector in the domain, since when I take T of it, I get 0. You'll always know that under linear transformations, zeros map to zeros. So the 0 vector is always in the kernel. It's always in the null space of A. But what about other vectors? If I got a vector inside of V, when I take T times U and I get 0, that vector V is in the quote-unquote kernel of T. Again, other terminology, the range of T. The range of T is also known as the column space of matrix A that represents T. So we're getting similar names, but we're looking at now a linear transformation as a mapping versus as a matrix. So the range of T is also known as the column space of matrix A that represents the transformation T. So the range of T is equal to T of U such that U came from V. It's the mapping where T goes from, range. So if you look at this, and I got vector space V, and I got another vector space W. T is the mapping that takes V into W. Does that make sense? So, to be in the range, this is kind of like your domain. It's all the vectors that are going to get mapped, and the range is all the vectors that get mapped to. So, the range of T is the TU, so you've got a U vector over here. And over here, when you map him, he's going to be T of U. So these are all the little vectors, T of U for any U inside of V. That's what it means to be in the range. It's these guys over here. And you may not cover all of W. You may only cover part of W, maybe the top part or the bottom part. But remember, it will be a subspace of W. Does that make sense? Just terminology. So when you hear the word kernel of a mapping is all the elements in the mapping that map to 0. Now, let's kind of tie back from an education perspective. You've been playing with kernels your whole life. You just didn't know it. When you were in, let's see here, high school, 10th grade or 11th grade, whenever you took Algebra 1 or whatever they're calling it now, Math 1 or whatever it's called. You remember taking polynomials and setting them equal to 0 and solving for x, okay? You know it better as roots, zeros, or x-intercepts. That's also known as the kernel of whatever the function that you're playing with and stuff. So we got fancy names for the same old stuff. Zeros, roots, x-intercepts, whatever you want to call them. It's still the same thing. It's the guys that map to 0, okay? When I plug it in, I get 0 out of it. So terminology, don't let it confuse you. All right, let's keep going. Section 4.3 here. All right, section 4.3 is working in the wonderful world of linear independence sets and bases. So we're gonna come back and beat to death these concepts again. All right. Now, let me set the stage here for your notes and for your brain. We are trying to look for linearly independence and the idea of basis. We've talked about basis before, but we're gonna hit them very hard on the purpose of why we want a basis. The idea is to look at these sets which span a particular vector space and to make it most efficient. We're looking for efficiency, okay? Making it very efficient. And by efficient, you'll understand the concept in just a second. So you know what a vector space is. It's the span of a set of vectors, all the linear combinations of a set of vectors. But that may not be the easiest or the most efficient way of writing it. So, first thing we're going to do is talk about the definition of linearly independent. Okay? So, linearly independent. Given a set of vectors, V1, comma, V2, dot, 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 VP, these are vectors in vector V, vector space V. To see if this is a set of vectors that are linearly independent, and we're math people, so I have to abbreviate it, so go ahead and introduce my code here. L period, I period. Linearly independent. The other term, if they're not linearly independent, they're going to be called linearly dependent. L period, D period. We're math people, don't think too deep in this. Okay, so with that concept, here's the deal. Okay? To see if they're linearly independent, what we want to find is, what we want to do is find constants C1, C2, C3, CP, such that C1 times vector V1 plus C2 times vector V2 plus plus CP times vector VP is equal to 0. Now, here's the big deal. If these vectors, V1 through VP, are linearly independent, there is only one answer that you can get. You can't have multiple answers. There's only one answer. And that is, if C1 is equal to C2 equals C3 equals all the way up to CP, and they're all equal to 0, is the only solution, and that's the key word right here, only solution to this system of equations we have over here, then these vectors, V1, V2, dot, 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 to VP, are linearly independent. So, anytime someone gives me a bunch of vectors and asks me, hey John, is these vectors linearly independent or not? First thing I'm going to do is I'm going to put mentally C1 times the first vector plus C2 times the second vector plus dot, 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 plus C3 or Cn times the last vector, Vn. I'm going to set it equal to 0, and I'm going to go try to find what Cn, the C1s and C2s are going to be. If all the C's are equal to 0, well, then it's linearly independent. If I get any other answer, which means free variables when I'm solving for this thing, then they're going to be linearly dependent. The only answer I can get is C1 equals C2 equals, they're all equal to 0. So, otherwise, the vectors will be called linearly dependent. So, big old theorem right here says this. If V1 vector, comma, V2 vector, comma, VP vector is a set of vectors 2 or more, I mean, you can have 2 or more, but you gotta have at least 2, okay? And they're linearly dependent if and only if, now I'm gonna talk about some math stuff here. I'm trying to get you guys set up, like you mentioned before. This is a 2000 sophomore level class. We're gonna get you into the junior and senior level classes when we get into the higher level math stuff. Math people have come up with their own language for doing stuff and different formulas. Here's one right here. You see this letter right here? IFF. Math people, this is what they write, IFF. What IFF stands for is if and only if. For you computer science majors out there, you may know it better as the double implication, okay? That's what it means, if and only if. I can go both ways on this one. For some j greater than 1, the vector Vj is a linear combination of the V1, V2, Vj minus 1, Vj plus 1, you skipped over Vj there, plus Vp, assuming that the V1 is not equal to 0, okay? You've got to be non-zero, the Vj is not equal to 0 here. So, linearly dependent means I can write this vector as a linear combination of the other vectors. That's what it means to be linearly dependent. Linearly independent means that I can't, which means if I set all these equations equal to each other, basically, the only way they're gonna be equal to each other is all the coefficients have to be zero. You know, zero always equals zero, but if that's your only answer, then they're linearly dependent, linearly independent, okay? Linearly dependent otherwise. Okay, so note, in a general vector space, we are not always, okay, able to put vectors into a matrix and row reduce. Okay, well, I can make up some really strange stuff, and then how are you gonna figure out how to put this stuff into a matrix? So this is more of an idea type thing here. But when we want to sit there and talk about vector spaces, basically, we wanna look at what we call the basis of these guys here. So, got some questions for you. Here we go. Got two questions here, two examples, but let me put this one down here and so you guys can see it a little bit better here. Here it is right here. So, let me see if I can't mess with your brain a little bit. And let's talk about this example here. I'm gonna let P, and I put a subscript on it, P1 of T equal 1. P2 of T is equal to 2 minus T. P3 of T is equal to T plus 2 plus T. So I got P1 of T is equal to 1, equal to 2 minus T, and P3 of T equals 2 plus T. Are the vectors P1, T, P2 of T, P3 of T, are they linearly independent or dependent? Well, these are polynomials. So this is a polynomial space, but it's still a vector space. There's a space of polynomials. Okay? So, here's the deal. Basically, are they linearly independent or not? So, how do I figure it out? If we go for the Li, and we don't know, put a question mark right here. Basically, if I set C1 times P1 of T, plus C2 times P2 of T, plus C3 times P3 of T, and I set that equal to 0. If they're linearly independent, the only answers I can get are C1 is 0, C2 is 0, C3 is 0, so forth and so on. However, you know, if I put this stuff in here, you know, the C1 times the vector of 1, equation 1, plus C2 times 2 minus T, plus C3 times 2 plus T, will that, if I try to set it equal to 0, is there any other solutions except the C's are all going to be equal to 0? Okay? But what you should notice is this. Also note, okay, solve for C's. But also note this. Now look at these guys. I can sit there and look at P3 of T, and can you actually write it as a linear combination of basically a constant? I'll use a different constant. I'll use it as K's. K times P1 plus a different K times P2. So in other words, can you get P3, which is 2 plus T? Would that be equal to K times P1 would be 1 plus K times P2 is 2 minus T. Can you solve this guy? This would be linearly dependent. So I'm trying to kind of distinguish between the two. When you think they're linearly independent, go this route. If you think they're linearly dependent, go this route. And solve for K, and K can't be equal to 0. If all the C's are 0, it's linearly independent. If all the K's are not 0, you can find constants, then they're linearly dependent. Well, I think I can do this here. Watch this. Now, in terms of this, we're going to combine like terms. So 2 plus T is equal to plus 2K2 minus K2 times T. Now, I can rewrite that as K1 plus 2k2. That part right here, they don't have a t on it, and that's got to be equal to constant 2. And negative k2 of t has to be equal to t. So if negative k2 of t equals t, can you solve for k2? Well, wait a minute. You can divide by the t because the t's cancel out. That pretty much gives you negative k2 has, what does that make k2 equal to? Divide by negative 1, what do I get? I get negative 1. And when I back substitute, so k1 plus 2k2 equals 2. So k1 plus 2 times negative 1 equals 2. I can add both sides. k2 would be equal to 4. If I do my math in my head correctly here. What does this tell me right here? I can find coefficients in front of the two polynomials to be able to get the third polynomial. So are these three polynomials, are they linearly independent or linearly dependent? Linearly dependent. Because you can find constants that are not 0, therefore, 3 dots in a triangular fashion, therefore, the set P1 of t, P2 of t, and P3 of t are linearly. That is the answer, right here. Does that make sense? But this is the way you need to think about it. So I got another example. Question first. Yeah.
I think I'm missing something, but why didn't you use like minus the 2k to the 2? Like I was confused on like the algebra.
Okay. Over here.
Yeah.
All right. So I put P3, and I'm trying to figure out, is there a K1 times the first vector, or polynomial, plus K2 times the second vector, polynomial, that I can get the third vector, the third polynomial, C2 plus T. So I put a K1, P1 was 1, P2 is this guy here. What did I do? I distributed this guy. So I came up with 2 plus T is equal to K1 plus 2K2 minus K2T. I distribute K2. Now, systems of equations. This is a constant, this is the coefficient from the T. So if these two guys are going to be equal to each other, the constant 2 has to be the constant over here. K's are constants, but there's no T attached to any of this stuff. So 2 has to be equal to K1 plus 2K2. And I set myself up that equation. And then the other part, the T here, has to match the T over here because they're equal to each other. So you're setting like terms equal to each other, which means that, so I wrote it, the T over here is equal to a negative KT, K2T. Well, I can divide by T on both sides to get myself an equation, and that's what I did. So negative K2 equals 1, and that made it very quick. I can solve for K2. K2 is going to be a negative 1. It's not 0. And when I get a constant that's not 0, automatically I'm done. This sucker is going to be linearly dependent. But I went ahead and show you what the constants were going to be. K2 was going to be negative 1. Then I back substitute and got K2 to be equal to, I'm sorry, K1, that's a big one there, K1 to be equal to 4. And I told you what the constants were. And as long as I can get constants that are not 0, that's linearly dependent. If I solve this thing and the only constants I can get are 0 constants, then they're linearly independent. And that's what I want to emphasize with you guys. Does that make sense?
So you just put basically you just put K1 plus 2K2 equal to
2.
and then you put negative K2T is equal to T on the outside.
Right, and then I divided by T, so I can just get the coefficients. That meant negative K2 is equal to 1, and then made it very quick. I can solve for K2, negative 1. Then I can back substitute that into this equation and find what K1 is equal to 4.
That's how you that's how you use them together, because you got the negative
Right.
1 for K2, you put it back into the 1 below.
Right. Exactly right. Now take a look at this guy here. Next example. I'm going to give you two vectors. V is going to be the sine of t, and W is equal to the cosine of t. Okay? Are the vectors V, sine of t, W, cosine of t, are these guys linearly independent or dependent? Now here, I'm only giving you two vectors. That makes it a lot easier for this linearly independent, dependent stuff. When I give you three or more, we're sitting there talking about systems of equations and try to set equals zero stuff. With only two equations, it makes it a lot easier. So, but I gotta tell you what world or vector space these guys live in. So I'm also using this as an example to show you other types of vector spaces that aren't traditionally written in the form of matrices and vectors and stuff that you would think about the rows and column thing that we've been doing. For example, here. The vectors, sine of t and cosine of t, are they linearly independent or dependent? Where this is your space, C0, 1. The C stands for continuous function on the interval between 0 and 1. So this is the space of continuous function. So f is a function, little line means such that f is continuous on that interval between 0 and 1. And you can go through your definition of continuity. You can talk about the calculus definition of continuity. The limit exists, the functional value exists, and they're equal to each other for every point between 0 and 1. Or you can go through the old high school way of looking at it. I don't lift my pencil from the paper when I graph between 0 and 1 on these two functions. Either way you look at it, that's called continuous, and I'm happy either way. I actually like the high school mindset because it gives me a mental picture of what's going on here. But you know, we always have the limit definition as well. So these two guys are continuous functions, sine of t and cosine of t. Are they linearly independent or dependent? Well, if sine of t and cosine of t are linearly dependent, then you can take sine of t and that will be equal to some constant c times the cosine of t. Because I only got two vectors, that makes it a lot easier for me. I can write one vector as a linear combination of the other vector, which means it's got to be a constant times the other vector. Now, that's what it means to be linearly dependent. Again, two vectors. This is what I got. Once I got three vectors or more, I've got to write this combination of equations here. But with two vectors, basically is one vector a linear combination of another vector. In English, if I only got two vectors, is one vector equal to a constant times the other vector? Answer is either yes or no. Tell me what you guys know about trig. Now, I can manipulate trig all over the place, but everything in trig is based upon basically two functions. What are those two functions? Sine and cosine. And I can't get one from the other. Now, granted, I could do a horizontal shift of the cosine graph to get the sine graph by 90 degrees or pi halves for you radian fans and stuff like that. But is there any constant c out there that I can multiply times the cosine function to actually turn it into the sine function? Well, the answer is yes or no. Can you turn a cosine function into a sine function? You can. How can you do it? What? No. We're not talking about derivatives and stuff like that. I'm talking about just linear combinations. Is there a constant out there in the universe that you can multiply the cosine function by to actually equal to sine function? No, you can't. Now, again, I'll reiterate. Everything in trig is based upon two functions, sine and cosine. If I could turn sine into a cosine by a constant, then everything in trig would be based upon one trig function, like cosine or sine. No, you gotta have both of them. So, okay, since no such c exists here, then we say sine of t and cosine of t are linearly independent. There is no constant out there that you can multiply times a cosine to turn into a sine. I could do a horizontal shift, but that's manipulating with the t variable. If there's a constant in front, think about it. If you look at constants, multiply in front of the cosine, all it does is affect the amplitude. Go back and think about your trig classes and stuff like that from high school. That's what it affects is your amplitude and how the wave goes. There's no way to turn a sine graph into a cosine graph. Remember, sine, y equals the sine of t, is a wave that starts at the origin and then goes up, down, and back again, and keeps on waving. The cosine t-graph does this. It starts at the amplitude up here at 1 and then goes down. Yes, they're both ways, but how they start basically is the difference. And without shifting it around, I can't multiply any constant times this guy to turn it into this guy. Well, I want to multiply it times 0 to get that point of 0. Well, if you multiply the entire function times 0, every point becomes 0, not just that first one. So there is no constant that I can multiply this guy by to turn it into this guy. So that's why they are linearly independent. So, but my point to this exercise is also to show you I've got polynomial vector spaces, I've got continuous functions on the interval between 0 and 1 vector spaces. There's a lot of different kind of vector spaces than just R2, R3, R4, R405, R2906. Yeah, those are great vector spaces. They're all vector spaces, but there are other vector spaces out there as well. Now, getting into the big definition here. Basis. H is a subspace of some vector space B. So let's let B, or beta, because we like to do Greek letters on this stuff, so that's a beta, is equal to a vector B1, comma, vector B2, dot, 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 vector BP. Is a set of indexed vectors in V. All right. Again, I'm throwing nice words to you guys to make this a much more higher level class than a class of freshman level class. Indexed. What does that mean? I put subscripts on this stuff, so you can recognize these guys. That's what index means. All right, so there's a V1, there's a V2, there's a VP. It's not just a gas station. It's BP. Okay, that's vector P out of the list of them. Does that make sense? That's what it means to be indexed. So again, don't think too high on this, but we do have terminology at this higher level to understand this material. So, these are indexed vectors, okay? B is a basis of, or for, however you want to describe that, the space H, if two things happen. B of 1. B is linearly independent. These set of vectors are linearly independent. So if you're going to have a basis for a vector space, the first thing is you look at those vectors and they have to be linearly independent. So any linearly dependent vector, you chunk him out. So you're only going to focus on the set of linearly independent vectors. And number 2, when you take the span of those linearly independent vectors, the span means all the linear combinations of those guys, you should actually get the entire subspace back. So I can't throw something out that's actually needed. So I've got to actually have a set of linearly independent vectors that when I span them, take all the linear combinations I can of these vectors, I should be able to get any vector in that's actually quote unquote in my subspace. Okay? This is what it means to be inside of vector space. Now this set B is clearly, it's contained inside of H, because these vectors come from H, but when I take the span of them, I should be able to get all of H. So, again, I want to talk about a definition and more of an example here. You talk about the standard basis, and I'm reiterating a bunch of stuff I've already talked about before, way back in chapter 2, 2.8 more specifically, but we're going to dive into this stuff deeper. The standard basis for Rn are these guys. So Rn is your n-dimensional vector spaces. So every vector has n components to it. So the standard basis for the Rn is going to be the vector E1, you put 1 in the first position, 0s the rest of the way. Vector E2 is 0, 1, you put a 1 in the second position, 0s everywhere else. Vector E3 is putting a 3 in the third, putting a 1 in the third component, and 0s everywhere else. And then dot, 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 all the way down. En, you put 1 in the nth component and 0s everywhere else. And notice something or other. If I actually take my vectors that are my standard basis of Rn, And I actually put them in an augmented matrix with all these vectors, put them in column space, if you will, what matrix actually shows up? 1, 0, 0, 0, 0, 1, 0, 0. What do you call that matrix? The identity matrix shows up. So this is directly connected to the identity matrix. This is your standard basis for Rn. All right. So, more problems for you guys. Another example. Let V1 be the vector 1, negative 2, 0. V2 be the vector 2, 1, 1. V3 be the vector 0, 3, 0. Show that V1, V2, V3 is a basis for R3. Okay. To be a basis, you got to be what? The first thing in your definition of a basis. Linear what? Linearly independent. The first thing you should think of in terms of the word basis is linearly independent. That's what you need to show. How do I show it's linearly independent? To show linearly independent, basically I would do C1 times your vector V1 plus C2 times vector V2 plus C3 times vector V3. Now I've got three vectors. And I'm going to set it equal to the 0 vector. And if they are linearly independent, what is the answer that I'm going to have to get for C1, for C2, and for C3? What do these constants have to be equal to? 0. If anything else, they're linearly dependent, right? So, this means that C1 times the vector 1, negative 2, 0, plus C2 times the vector 2, 1, 1, plus C3 times the vector 0, 3, 0. That's got to be equal to the 0 vector. You with me? 0, 0, 0. Now, what I want you to do is solve for C1, C2, and C3. How would you do that? Based upon all the stuff we've covered, you know, 2/3 of the way through the semester here, tell me, how would you solve for C1, C2, C3? What would you do? Augment matrix, right. So you end up getting 1, negative 2, 0, 2, 1, 1, 0, 3, 0, augment with 0, 0, 0, and now tell me what you're going to do. Or reduce. R-R-E-F. I would take this guy, sweep down and kill him. Okay? Then I'll find a pivot here, sweep down and kill him. Then I get a pivot down here, sweep up and kill the two above it, and take this guy and sweep up and kill the other. Does that make sense? But for the sake of time, I'm going to tell you what the RREF is. And when I do RREF, I get this. 1, 0, 0, 0, 1, 0, 0, 0, 1. Augment 0, 0, 0. What is this telling me? This is what, well, no, first off, it tells me what? C1 is equal to 0. C2 is equal to 0. And C3 equals 0. That's what the matrix is telling me. Now, what does this tell me? That C1 equal to 0, C2 equal to 0, C3 equal to 0. The vectors are linearly independent. Does that make sense? Now, okay. So, the vector set V1, V2, V3 are independent. Okay? So, first off, I got to be linearly independent. That's part one on showing you have a basis. What is part two on showing you have a basis? Well, part two is actually down here. Since these guys are now linearly independent, is the span of V1, V2, V3 going to be equal to all of R3? That's what part two of being linearly independent you need to show. Which means this. Let W be a vector of R3. such that W is equal to something very arbitrary. It's R3, so I gotta have three components. What are my three components? Just to completely blow your mind, let's go Greek. Alpha, beta, and gamma, okay? Some arbitrary, very arbitrary constants here. Alpha, beta, gamma. What is the relationship between W and the V1, V2, and V3? That's the big deal, okay? So, here's the idea, just to inform you. All right, so, W is equal to this guy. So, what's the relationship between the two? Well, I can take C1 times vector V1 plus C2 times vector V2 plus C3 times vector V3, and that's going to set it equal to the W vector. And I should be able to solve for these constants, C1, C2, and C3, so I can actually get W, right? Because W is very arbitrary in R3. So if I can get anybody, if I can find these C1, C2, C3, that I can do this and get W out of it, I can get any vector in R3. That's my point, because this is arbitrary. So how do I do that? Well, this means that C1 times 1, negative 2, 0, plus C2 times 1 plus C3 times 0, 3, 0 is equal to alpha, beta, gamma. Okay? So how would you solve for this C1, C2, C3? Solve for C1, C2, C3. What would you do? Augment matrix. Catch a pattern, chapter 1. Augment the matrix here. So, this would be 1, negative 2, 0, 2, 1, 1, 0, 3, 0. Augment with alpha, beta, gamma. Now, with alpha, beta, gamma, now your calculator is pretty much useless at this point. What do I need to do? I want to do RREF. You with me? And if I do RREF, I'm going to get this. 1, 0, 0, 0, 1, 0, 0, 0, 1. And I'm going to get basically some kind of number over here for this part, which will be based upon alpha, beta, gamma, and some constants. A number over here, too, based upon alpha, beta, gamma, and a number over 3 over here at alpha, beta, gamma. Once I get this, I could show you that this is literally dependent. Well, this arbitrary vector is literally dependent on these guys here. So, once you get this right here, this will imply, once you have to show me this implies that any W in R3 can be written as a linear combination of B1, B2, and B3. And once you got that right there, this much room to write on. Therefore, 3 dots in a triangular fashion means therefore, between part number 1 and part number 2, the set of vectors V1, V2, and V3 are a basis for. Does that make sense? Well, geez, Dr. Taylor, how do you actually find these guys? Well, that's your homework for tonight. I want you to sit there and take this guy, row, reduce, sweep down, get a pivot, and see what happens over here. And you're going to get some awful looking equations over here. They're not really equations. They're constants times alpha plus constant times beta plus constant times gamma. Over here, everything's going to be based upon alpha, beta, and gamma. But you're going to get these guys. Alpha, beta, gamma represents arbitrary numbers. So you've actually got what the C1, C2, and C3 are. So study up on that. And we'll finish up with these idea of these vector spaces next time. And then we're going to be in the basis. And then we're going to be moving on into the concept of 4.4, which is coordinate vectors and stuff. So study hard, and I'll see you guys